Yellowstone supervolcano eruptions were produced by gigantic ancient oceanic plates. This is what a study finds. This is by Virginia Tech on Science Daily. The long-dormant Yellowstone supervolcano in the American West has a different history than previously thought, according to a new study. This is dated 2018, July 26. The long-dormant Yellowstone supervolcano in the American West, one of the most dangerous supervolcanoes in the world, has a different history than previously thought, according to the new study by Virginia Tech geoscientists. Scientists have long thought that the Yellowstone caldera, part of the Rocky Mountains and located mostly in Wyoming, is powered by heat from the Earth's core, similar to most volcanoes such as the active Kilauea volcano of Hawaii, which sits over a hotspot. But new research published in Nature Geoscience by Ying Zhu, an associate professor with Virginia Tech College of Science Department of Geoscience, shows a different past. Zhu said, in this research, there was no evidence of heat coming directly up from the Earth's core to power the surface volcano at Yellowstone. Instead, the underground images we captured suggest that Yellowstone volcanoes were produced by a gigantic ancient ocean plate, an oceanic plate that dove under the western United States about 30 million years ago. This ancient oceanic plate broke into pieces, resulting in perturbations of unusual rocks in the mantle, which led to volcanic eruptions in the past 16 million years. The eruptions were very explosive, Zhu added. A theoretical seismologist, Zhu created X-ray-like images of the Earth's deep interior from USARA, part of the EarthScope project funded by the National Science Foundation, and discovered an anomalous underground structure at a depth of about 250 to 400 miles right beneath the line of the volcanoes. This evidence was in direct contradiction to the plume model, Zhu said. In her study, Zhu found the new images of the Earth's deep interior showed that the oceanic Farallon plate, which used to be where the Pacific Ocean is now, wedged itself beneath the present-day western United States. The ancient oceanic plate was broken into pieces just like the seafloor in the Pacific today. A section of the subducted oceanic plate started tearing off and sinking down to the depths of the Earth, and the sinking section of the oceanic plate slowly pushed hot materials upward to form the volcanoes that now make up Yellowstone. Furthermore, the series of volcanoes that make up Yellowstone have been slowly moving, aging so ever since. The process started at the Oregon-Ohio border about 16 million years ago, propagated northeastward, forming a line of volcanoes that are progressively younger as they stretch northeast to present-day Wyoming, that is Yellowstone Supervolcano, Zhu added. The previously held plume model was used to explain the unique Yellowstone hotspot track, the line of volcanoes in Oregon, Idaho, Wyoming, that dots part of the Midwest. And we know that the one in southwest Idaho is in fact a supervolcano. Now, the Wyoming that dots part of the Midwest, if the North American plate was moving slowly over a position-fixed plume at Yellowstone, it will displace older volcanoes towards the Oregon-Ohio border and form a line of volcanoes, but such a deep plume has not been found, Zhu said. So what caused the track? And Zhu intends to find out. Quote, it has always been a problem there. The scientists have tried to come up with different ways to explain the cause of Yellowstone volcanoes, but it has been unsuccessful, she said, adding that hotspot tracks are more popular in oceans, such as Hawaii Islands. The frequent geyser eruptions at Yellowstone are, of course, not volcanic eruptions with magma, but due to superheated water. The last Yellowstone super eruption was about 630,000 years ago, according to experts. Zhu has no predictions on when or if Yellowstone could erupt again. The use of the X-ray-like images for this study is unique in itself. Just as humans can see objects in a room when a light is on, Zhu said seismometers can see structures deep within the earth when an earthquake occurs. The vibrations spread out and create waves when they hit rocks, and the waves are detected by seismometers and used in what is known as diffraction tomography. Zhu said this is the first time the new imaging theory has been applied to this type of seismic data, which allowed us to see anomalous structures in the Earth's mantle that would otherwise not be resolvable using traditional methods. Zhu will continue her study of Yellowstone. She said the next step will be to increase the resolution of the X-ray-like images of the underground rock. More detailed images of the unusual rocks in the deep earth will allow us to use computer simulation to recreate the fragmentation of the gigantic oceanic plate and test different scenarios of how rock melting and magma feeding systems work for the Yellowstone volcanoes. The story sources materials provided by Virginia Tech. Heat from below Pacific Ocean fueled Yellowstone, study finds, and is still fueling Yellowstone. University of Illinois Urbana campaign. Recent stories in the national media magnifying fears of a catastrophic eruption of the Yellowstone volcanic area, but scientists remain uncertain about the likelihood of such an event. To better understand the region's subsurface geology, geologists have rewound and played back a portion of its geologic history, finding that Yellowstone volcanism is far more complex and dynamic than previously thought. The heat needed to drive volcanism usually occurs in areas where tectonic plates meet and one slab of crust slides or subducts under another, but Yellowstone and other volcanic areas in the inland western U.S. are far away from the active plate boundaries along the west coast, said geology professor Li-Yun Liu, who led the new research. He said in these inland cases, a deep-seated heat source known as a mantle plume is suspected of driving crustal melting and surface volcanism. In the new study reported in the journal Nature Geoscience, Liu and graduate students Quan Zhu and Jiashun Hu used a technique called seismic tomography to peer deep into the subsurface of the western U.S. and piece together the geologic history behind the volcanism. Using supercomputers, the team ran different tectonic scenarios to observe a range of possible geologic histories for the western U.S. over the past 20 million years. The effort yielded little support for the traditional mantle plume hypothesis. Quote, our goal is to develop a model that matches up with what we see both below ground and on the surface today, Zhu said. We call it a hybrid geodynamic model because most of the earlier models either start with an initial condition and move forward or start with the current conditions and move backwards. Our model does both, which gives us more control over the relevant mantle processes. One of the many variables the team entered into their model was heat. Hot subsurface material, like that in a mantle plume, should rise vertically outwards towards the surface. But that was not what the researchers saw in their models. Quote, it appears that the mantle plume under the western U.S. is sinking deeper into the earth through time, which seems counterintuitive, Liu said. This suggests that something closer to the surface, an oceanic slab originating from the western tectonic boundary, is interfering with the rise of this plume. The mantle plume hypothesis has been controversial for many years, and the new findings add to the evidence for a revised tectonic scenario, the researchers said. A robust result from these models is that the heat source behind the extensive inland volcanism actually originated from the shallow ocean mantle to the west of the Pacific northwest coast. Liu said this directly challenges the traditional view that most of the heat came from the plume below Yellowstone. Eventually, we hope to consider the chemical data from the volcanic rocks in our model. That will help us further constrain the source of the magma, because rocks from deep mantle plumes and near-surface tectonic plates could have different chemistries. As for likelihood of a violent demise of Yellowstone occurring anytime soon, the researchers say it's still too early to know. Quote, "Of course, our model cannot predict specific future super-eruptions. However, looking back through 20 million years of history, we do not see anything that makes the present-day Yellowstone region particularly special, at least not enough to make us suspect that it may do something different from the past when many catastrophic eruptions have occurred," end quote. And Liu went on to say, "More importantly, this work will give us a better understanding of some of the mysterious processes deep within the Earth, which will help us better understand the consequences of plate tectonics, including the mechanisms of earthquakes and volcanism." Story source is materials provided by University of Illinois at Urbana-Champaign. Written originally by Louis Yoxulian. If you'd like to join me on my Patreon account, you will hear content not covered by mainstream media. These riveting stories will be based on my research, and I will state my opinions and give my personal insight on diverse and controversial subjects and world events not covered by mainstream media, and not supported by YouTube guidelines. So whatever I have on my Patreon, most of those will not be on my YouTube channel. Please consider becoming a member today. More of the most significant and important videos will be on my Patreon channel. Your support helps me to continue my research and keeps this YouTube channel alive. And we depend on your support, your generous charity, because we help economically challenged families here in Athens, Greece, in Kapota, and we also help the young generation with university tuition and the community around our church. Thank you.